I guess that's it. Good. We're very happy to have a discussion now with Shu-Heng, Ryan, Kantaro, and Zohar about non-invertible symmetries. So Shu-Heng, take it away.
All right. Thank you. Thanks the organizers for putting together this very interesting and exciting conference, and for inviting me to be one of the panelists on non-invertible symmetry. And since this is a panel discussion, I figure I should talk about something that I don't understand rather than something I do. So I will share some preliminary thoughts that I learned from talking to Sahang Safshnari and Yifan Wang. This is not a research seminar, and this is supposed to stimulate discussion. So let me get started. It will be about continuous non-invertible symmetries. So the first slide is very easy. We all know that for continuous ordinary global symmetry, we can define it in terms of the conserved local Noether current. And for continuous Q-form symmetry, we will have a higher a current that is a d minus q minus 1 form, obeying the conservation equation. And we take that current, we integrate it on the appropriate manifold, we get a conserved charge, which is topological in Euclidean spacetime. What about continuous non-invertible symmetry? I think in the past 2 days, we have heard some examples of discrete non-invertible symmetry, but it would be interesting to see if there are continuous ones. And in fact, there are, and the constructions are very easy. And the particular example that I will talk about have been discussed in these 2 papers. And it's about the continuous non-invertible symmetry in the ordinary 1 plus 1D C equals to 1 orbital theory. So it's the CFT whose target space is an interval. So to start with, let's start with the C equals to 1 free compact boson CFT, whose target space is a circle. And phi is the target space field. It's 2 pi periodic. There's a U1 global symmetry, which let me call it the momentum symmetry, that shift phi just by a constant. And that leaves all the action invariant. That's just an ordinary U1 global symmetry. There's a Noether current, which is proportional to the Hodge dual of d phi. Here, r is the radius of the target space circle. And this theory has this invertible U1 symmetry. It comes with a continuous family labeled by this alpha, and alpha is 2 pi periodic. So far, everything is standard. And the next thing you do is very simple. You just consider a Z2 global symmetry of the compact boson that flips the sign of phi. And you subsequently gauge this Z2 charge conjugation symmetry, C. The resulting theory you get is usually called the orbital CFT with target space S1 mod Z2. The U1 momentum symmetry, the one we were talking about on the previous slide, obviously got broken by the orbital because phi flip sign under the gauging, the current is linear in phi, so the current also flips sign, and therefore the exponential I alpha j becomes exponential minus I alpha j. But while the U1 symmetry is broken, we can just consider the cosine of that charge. And that obviously survives as a topological operator in the resulting orbital theory. So let me denote this cosine line by this funny symbol n alpha. It comes with a continuous family alpha that used to label the angle of the U1 symmetry. So the slogan is just that the exponential is invertible, but the cosine is not. And in the orbital CFT, this continuous family of the cosine lines obey this non-invertible fusion rule. It's non-invertible because when we multiply 2 of these objects, we get more than 1 term on the right. So this is a very simple way to obtain a continuous non-invertible symmetry. There's an interesting point that was made in this paper, that when the angle is 0, naively you would think the cosine line just gives you 2 copies of the trivial line. But it's actually not true in the orbifold theory. It's 1 plus eta, where eta is the quantum Z2 in the S1 mod Z2 orbifold theory. So let me remind you that in 1 plus 1D CFT, if you gauge a Z2 global symmetry, in the orbifold theory, there will be a quantum or dual or orbifold Z2 symmetry. You can think about it as an emergent Z2 symmetry in the orbifold theory. And this eta is the Z2 for the quantum Z2 of the orbifold theory. So before the orbifold, we are in this compact boson CFT. We have a local operator. That's our conserved Noether current, from which we can build topological charges and get the U1 symmetry operator. After gauging, the current now is no longer a local operator. By local operator, I mean an isolated point in space-time. But after we gauge the Z2, the current is not gauge invariant. So rather, it lives at the end of a Z2 Wilson line. The Z2 Wilson line is precisely this eta line. So after gauging, J now lives at the end of the Z2 Wilson line. But since in the fusion of this non-invertible cosine line, we have an eta, that means J also lives on the non-invertible line. So you cannot bring this point out. It's kind of stuck on this non-invertible N alpha line. And the perspective that was advocated by Ryan and Yifan was that the non-local current living on the non-invertible line should be thought of as the reason why we have a continuous family of non-invertible lines. We should think about it as a non-local Noether current. It has scaling dimension 1, and the spin is also 1. Generally, for a conformal line, you can only talk about the scaling dimension, but not its spin. But here, we are talking about a topological line. And the topological line commutes with the left and the right moving Virasoro, so it's sensible to talk about its spin as well. In particular, this non-local operator that's stuck on the line obeys the conservation equation, the ordinary conservation equation for a 1 plus 1D current. And the purpose of life for this non-local current is that you can integrate J, not arbitrarily in your space, but along this non-invertible line. Since it has dimension 1, it triggers a marginal defect flow on the line, and presumably, and in this case, will generate the continuous family of the non-invertible line. So the upshot is that we should not only, when we are handed the quantum field theory, we should not only look for local current obeying conservation equation, but also those non-local ones that are stuck on the lines. And maybe they will teach us something about some hidden family of non-invertible lines. So one question that we can discuss is that for ordinary local currents, we can couple them to background gauge fields. For the non-local one, I'm not sure how to do that. So that brings me to the end of my talk.
Could I ask a question?
Yeah.
Hi, I'm from Edinburgh. When you mentioned the holomorphic derivative of J, how do you take that derivative if the thing is stuck on the line?
So you can define the line is topological, means that if I compute any correlation function, I can move it a little bit without crossing any other operator, and that wouldn't change the, well, if I only move the line itself, that wouldn't change the correlation function. But since here I have an insertion.
I should imagine I wiggle the whole line.
Yeah, I just wiggle the whole line. Okay. Yeah, that defines a function of z and z bar, and then I can take the derivative.
Okay, great. Thank you.
Okay, so I'll just end my talk with 2 questions that hopefully stimulate some discussion. So before I was talking about a specific example of the orbifold CFT, but let me ask, given a general topological line in 1 plus 1D, suppose somehow I just happen to know there's a scaling dimension 1, spin 1 non-local current that's stuck on it. Does that always lead to a continuous family of topological lines when I integrate it along the line? That's not immediately obvious to me, because for such a deformation to preserve the topological nature of the line, it in particular has to be exactly marginal. But for ordinary local current, we can show the exact. So here, it's not that obvious that it generates an exactly marginal flow because the currents are stuck on the line. So for example, if you want to compute the three-point function of this non-local currents along the line, conformal symmetry doesn't tells you it has to vanish. In fact, generally, I don't think it vanishes. So there are some conditions you have to check to make sure such a current does generate a continuous family of non-invertible lines. This kind of bothers me because for ordinary symmetries, if you hand me a local current and you tell me it satisfies a Noether conservation equation, then I'm all set. I just take that current, I integrate it on some manifold, I get a topological charge, and I know there's a symmetry. But for this non-local current, at least it appears to me that there's some more work, that extra work to do to ensure that it really gives us a continuous family of non-invertible line, and I don't understand it fully. Finally, in the example that I gave, the continuous non-invertible symmetry, you can say is a little bit trivial because rather than talking about this weird cosine line, I know where it comes from. It comes from the U1 symmetry before the orbifold. And I can understand everything before the gauging and then refuse to talk about this non-invertible symmetry at all. So of course, the non-invertible lines still have various interesting dynamical consequences, and that's what Yifan and Ryan explore in their paper. But it will also be interesting to see if there's any genuinely non-invertible continuous line that there's just no way that you can get it from an ordinary global symmetry via gauging. I have some preliminary thoughts with Yifan and Shu-Heng of finding such a family in rational conformal field theory, but the first question is more basic and has to be settled. Okay, I'll end my discussion here, and I'll hand it to Zohar, right? It's stuck on the line. It's not a local operator. By local operator, I mean an isolated point in space-time. But this guy is not. It's stuck on the line.
But besides having the line, it doesn't produce any further non-locality. So it's just like local on the line, right?
Yeah, it's a point on the line.
So following up on that, I can point out that terminology is like to confuse a lot of us because in the topological field theory, you think of that as completely local. We do have a notion of defects, embedded defects, and things like that. And then sing the song again. All of those can be covered under the umbrella of the Komargodski hypothesis.
Right.
Staying in the topological context.
Yeah.
So we think.
I think the term local is still.
Thanks also to the organizers for this opportunity to present some little thoughts, mostly some work in progress and a summary of little work from last year. Notice that this is also with Shu-Heng. Maybe Shu-Heng should have given all the talks. Okay, I'll talk about some applications of non-invertible symmetries. So Shu-Heng and also previous talks gave an introduction of what non-invertible symmetries are. I'm not going to explain what that is, but I'll just tell you a few facts that are good to know about applications of non-invertible symmetries for the dynamics of some interesting systems in 1+1 dimensions. So the first example is a non-abelian gauge theory. So it's an SUN gauge theory with a fermion in the adjoint representation. It's a single fermion in the a single non-chiral Majorana fermion. And it's a system that many people studied in the 80s, 90s, and also very recently. It's a strongly coupled gauge theory in 1+1 dimensions, and there is some hope that they would capture some interesting phenomena like confinement and some such things. Now, in this slide, it's a massless. I've taken the fermion to be massless. I'll say a few words about the massive theory. So this theory has few symmetries that are completely obvious. One is just the chiral Z2 symmetry that flips its left-moving fermion number symmetry. And the other is a one-form symmetry. A one-form symmetry in this context is just topological local operators, ON, so their correlation functions are position independent, and they satisfy this rule. So the question about such theories is that given that they have this one-form symmetry, namely they have local operators which are space-time independent, you can classify various states or vacua of this theory by the expectation values of these topological local operators. And because this topological local operator has to exponentiate to 1 if you raise it to the power n, there are n universes. Sometimes people call that universes, sometimes they call it sectors. These are various vacua of the theory with different expectation values for this topological local operator. So if you draw a qualitative picture of the Hamiltonian of this theory, there are some vacua with k equals 0, some vacua with k equals 1, some vacua with k equals 2, and so on. Okay? And you, in principle, to solve this theory and to understand fully the dynamics of this theory, you must understand the vacua in each of these sectors or universes. And physically, we're very interested in that because the physical meaning of these various sectors is the ground state of k strings. So if you put on the lattice, you could put this model on the lattice, you could decide that you want to study the dynamics of k strings, then those are the possible ground states of those k strings. Okay? Now, so physically, the most interesting question, one of the most basic questions, is what are the energies of the lowest states as a function of k? So if all the energies for every k are all the same, if these sectors all have exactly the generate energy density, we could say that the strings, when we put k strings, then they basically almost annihilate to the vacuum and there is no tension. Otherwise, we call it string tension, and this is measured in the lab, and it's also measured in Monte Carlo simulation. So this 1+1 dimensional model could capture some interesting such things. Okay, so that's what I just said. The energy density in these ground states is related to what physicists call the k-string tension, and it's a basic observable in many Monte Carlo simulations of Yang-Mills theory. So for many years, people have debated whether this theory has a picture like that, meaning that you put two strings and they form some non-zero tension, or maybe it's all degenerate in the massless case. And it's not known. The symmetries of this theory are not strong enough to decide analytically, and Monte Carlo simulations are difficult for the massless case, and people have some results for the massive case, but not for the massless case. So the main point about this theory, which is what I'm bringing it up here, is that this theory has a huge number, actually exponentially large, exponentially huge number of non-invertible symmetries that are completely non-obvious in the Lagrangian formulation of this theory. So if you just write down this action, there is no way to see that it has an exponential large number of topological lines. But they exist, and using those lines, it was possible to finally solve this theory. And in particular, it was possible to prove that there is complete deconfinement, that if you put k strings, they have zero tension in the massless case. And further, so the result is that the low energy theory in the massless case is completely deconfined, and furthermore, it's a gap two-dimensional topological field theory of the Frobenius type. And it's possible to even determine that two-dimensional topological field theory. As a nice application of non-invertible symmetry, you can put back a small mass to try to make eventually contact with experiment or Monte Carlo simulations. And you can actually exactly compute the string tension for a very small mass. So when the mass goes to 0, this thing goes to 0, and all the strings are tensionless. But when the mass is non-zero, you get this nice formula, which is a nice concave function describing strings with a small binding energy. So it's a nice result. And actually, people that simulate Yang-Mills theory oftentimes model string tension with a Casimir formula, which is like k times k minus 1. And in this model, you get a sign, which is maybe a more refined prediction. And this is an exact prediction for small mass. We don't know how to extend this prediction to maybe not so small mass. So it's not yet known how to compute the second order. But for very small mass, that's the prediction. And to get this prediction, it requires like sophisticated 2D TFT techniques. So just to finish, today, I wanted to tell you a little bit of preliminary results on what happens when you have two adjoints. So the world of 1+1 dimensional gauge theories is riddled with these non-invertible symmetries. You can try to solve many models. So the model with two adjoints is a little bit richer. I'll just say a few things about it. In general, I don't know what this does, but for SU2 gauge theory, again, we found some non-invertible symmetries. And the conclusion for SU2 gauge theory is that it's gapless. And so there are two universes or two sectors, one with k equals 0, one is k equals 1, describing one string or zero strings. And they're both gapless, and they flow to the Lattinger liquid, or just a compact boson in high energy physics parlance, with this particular radii. And to obtain this radii, the consistency, the consistency of checking these things requires some non-invertible symmetries. And one interesting thing is that actually the two universes are separated by a topological line defect that's present in this theory. And that's how we know that it's completely deconfined as well. So the big question here is to try to get predictions for non-zero small mass. And that's what we're hoping to be able to do using these non-invertible symmetries. But the bottom line is that gauge theories, especially massless gauge theories, or gauge theories with a very small mass in 1+1 dimensions, typically have a huge amount of non-invertible symmetries, which are non-obvious. And you can try to solve many such theories, in particular maybe the supersymmetric 1+1 dimensional theories and so on. And so that's it. That's all I wanted to say. Thank you.
Nani, while there's a transition, can you ask your question?
Yeah, how much of that can be determined with the less sophisticated methods? For example, the spectrum of the TQFT when it's gapped can be found easily. Also, the fact that it's not confining can be shown either with large number of flavors by doing 1/n, and then also for n=1, and therefore it's quite likely that that's the case for all n. So more generally, how much of that can be done without the more sophisticated methods?
Okay, thanks for the question. Yes, so the limit of many flavors, as you said, is probably possible to tackle with perturbation theory. So you're completely right. We can understand the limit of many adjoint fermions. However, the case of one adjoint fermion or two adjoint fermions, well, as you know, for the case of one adjoint fermion, there were conflicting results in the literature. There is no known way to analytically establish deconfinement without using these non-invertible symmetries, as far as I know.
Isn't it essentially the G mod G story?
The G mod G story is describing the physics of the zero string sector. To establish deconfinement, that's not sufficient. But if you want to understand the spectrum of vacua in the sector with no strings, that's indeed the G mod G story. But if you want to ask what is the tension of one string, that's not described by that. And there were conflicting papers, including by very prominent people, saying opposite things. So I don't know any way to prove that it's deconfined other than what I said.
Okay, we'll have more discussion after the talks, so we can bring it back. So, hello everyone. It's a pleasure to be here at this very nice conference, and I'm excited for the start of our collaboration. I want to talk a little bit about the bulk boundary correspondence, which I think you already heard a bit about in Xiaogang's talk. I'll give you my take on it. So there's if we're thinking about finite categorical symmetries, and I kind of want to be agnostic about dimension, although I really only know how to do one categories very well. That if we have a symmetry n category, so symmetry of a space-time n+1 dimensional theory, there's a natural n+2 dimensional state sum we can associate to it, which I'll just call the Tarayev-Viro model. Specifically, the Tarayev-Viro model was formulated in n=1. It's the same thing as this Levin-Wen model. And the way you define this model, so here I'll give you the n=1 definition, but you can iterate the dimensions as is apparent. You have co-oriented surfaces labeled by simple elements of the category, so symmetry operators. And then you have line junctions by morphisms where you compose these operators. And at point junctions, there is hiding this F symbol that we saw in some previous talks like Julia's, where you can draw a point junction like this, and if you slice it with a plane, you see there is this these black lines do this crossing equation move. And these F symbols define the weight of this diagram, this network of surfaces in the state sum, and we sum over all of these networks, and various nice properties of this crossing relation imply that this is a finite sum over topological classes. So for instance, if we study a category associated to a finite group, maybe with some non-trivial F symbol given by this group cohomology class, this is just another way of talking about 3D Digraph-Witten theory. So we know a lot about that theory. This state sum is literally just the sum over gauge fields. So you can kind of think about these co-oriented surfaces, or hypersurfaces in general, as defining some kind of gauge field for this symmetry N category. So this theory is very nice. Here's a proposition. This argument is from my paper with Yifan. So theories with categorical symmetry A are in bijunction with boundary theories of this theory, this Tarai-Vera theory, defined by the same category. We'll need some caveats here, but here's the argument, and you can fill in the caveats from the argument. So if we have a theory with the categorical symmetry, we can define a boundary theory of the state sum. All we have to do is say what happens when the surface meets the boundary. So if we go back to this picture, if the black plane is the boundary, so you can think of everything behind the plane as not existing, these surfaces are ending on these black lines, and we can just put there the topological operators that define our symmetry. And the symmetry rules of the boundary theory are also going to be given by the F symbols, and so there's no problem when this singular junction passes through the boundary. The state sum changes, but the boundary correlation function changes in exactly compensating way. So it's a good boundary condition. Conversely, you already have a boundary theory, then we can create a theory that exists not on the boundary of anything, where you have a categorical symmetry. And the way we do that is with a reference boundary condition, which we call Dirichlet. It's really like setting the gauge field to 0 on the other side. And in terms of the state sum, you just don't allow any of the surfaces to end on the other boundary. And by modifying this boundary condition slightly, so say imposing that a surface ends somewhere, that defines topological operators in the whole theory, and that's the action of your symmetry. And you can also show these are actually inverses of each other. So if we choose a different boundary condition, a different reference boundary condition, so here we chose some specific boundary condition, but there are many possible gapped boundaries, and they're all given by, they're classified by module categories of our symmetry category A. And if we do that, we get a different theory with actually a different symmetry. It doesn't have asymmetry anymore. Instead, it has this thing, which is like the commutant of A as it acts on M. And what we say is that these categories A and AM are Mourinho equivalent. And what it means is that if you're studying theories with asymmetry, you might as well be studying theories with AM symmetry. Like there's going to be a one-to-one correspondence of gapped phases, phase transitions. Actually, there's just going to be some duality mapping between them. So for instance, Vec G, so what you have associated to ordinary group symmetry, and Rep G, which is what you have associated to G gauge theory, are Mourinho equivalent, and the duality is just given by gauging. But there's some more weird-looking Mourinho equivalences. For instance, apparently theories with D8 symmetry are the same thing as theories with Z2 cubed symmetry with a certain anomaly. You wouldn't think that anomaly-free theories are the same thing as studying anomalous theories for a different symmetry group, but so they are. And the point here is that the bulk TQFT only depends on the Mourinho class of A. So all this data of lines, this state sum is just one way of presenting the same TQFT. If we use something Mourinho equivalent, it's the same. So when we are going to go to higher dimensions, there's less TQFTs in some sense. So it was recently showed by Lan and Wen, and Theo also has a version of the statement that TQFTs in 3+1 dimension are all some kind of gauge theory, up to some invertible piece. Okay, so this is not great for looking for interesting TQFTs, but it is also not great for looking for higher categorical symmetries. Well, the bulk boundary correspondence is a little bit puzzling. We really expect the TQFT to contain much more data than this result suggests. For instance, 2 plus 1D theories with a Zn1 form symmetry, they have anomalies that you can write in terms of, say, this 2 form B. We usually write this is the Pontryagin square. And this theory, so there are non-trivial anomalies for these symmetries, but when the level of the anomaly K is coprimed to 2n, the Turayev-Vero theory you get, which is essentially when you sum over B's, is an invertible theory. And actually, it's only sensitive to the signature of the four manifold. It's essentially a gravitational theta angle. So it doesn't seem to capture what we said, which is we said that essentially boundary conditions of such a theory should be the same as theories with one-form symmetry with this particular anomaly. It gets worse, of course. If you have a braided fusion category, such as a modular tensor category, this is something we would be interested in studying from the point of view of symmetries, because it defines a symmetry 2 category that could act on something like a Chern-Simons theory. It also defines some, in this case, the Turayev-Vero model is this Crane-Yetter-Walker-Wang model. And for any MTC, this theory is going to be invertible, and the partition function only again sees the signature. So is there a sense in which all MTCs are more or less Mourinho equivalent? Or is there something really hiding in this invertible piece? There you go. That's what I wanted to share. Now
could I ask a question here? So,
Go for it, Greg.
could I ask a question?
Yes.
So, what about topological field theories like Donaldson theory?
I don't know. What about them? That's not a Turayev-Vero theory.
Topological field theory. Sorry?
It's not a Turayev-Vero theory. I only talked about Turayev-Vero theories. So I also didn't include things like chiral Chern-Simons.
Sorry, I'm talking about the theorem you said that.
Yeah, but I was
All
only
3 plus
talking
1.
about Turayev-Vero theories. Like, I also wasn't including things like chiral Chern-Simons theory. Those boundary
I see.
conditions are more delicate. They also have gravitational anomalies. So that was one of the caveats that is in the theorem.
Is unitarity also part of that theorem? When you're defining a TQFT for that, are you assuming it's unitary?
Your hypotheses.
Unitary doesn't really seem necessary to me. It's
Like, I'm not sure that this LAN1 classification that I worked on is a blow or not. It's a classification of a particular class of semi-simple TQFTs, but it's a classification of only, like, very explicitly, it is not a classification of actual TQFTs. It's a classification up to invertible phases. And so it could very well happen that there's a lot going on in the invertible phases, which are just explicitly not part of the problem in that classification.
But Theo, just to clarify, you're also assuming unitary, yeah?
No, I'm assuming very strong semi-simplicity assumptions, which I think would follow from unitarity. But it's an algebraic statement.
But it's even worse because I think most physicists would say there just are no non-trivial invertible theories in 4 dimensions because this theta angle can always just be tuned to 0.
Yeah. I mean, algebraic, like it is a statement in algebra about non-degenerate braided fusion 2 categories is what that actual statement is.
Okay, let's watch Kantaro's video and then we'll get into this in more detail.
Hi everyone, I'm Kantaro Ohmori from University of Tokyo. I first thank organizers for their enormous efforts. I'm sure the meeting is running wonderfully, and I also appreciate that I could present this video later in front of the great audience of the meeting. Here, I'd like to talk about non-invertible symmetries or categorical symmetries in 3+1 dimensions, which is a research area in its infancy. And therefore, we have to ask the very basic question of is non-invertible or categorical symmetry useful, meaningful, physical, interesting, or whatever in 3 plus 1 dimensions, or more generally, dimensions higher than 1 plus 1. In 1 plus 1 dimensions, there are pretty much of positive evidences. Some of them are conveyed by Shu-Heng and Zohar. But in higher dimensions, I would even start from asking, does non-invertible symmetry exist? An answer, of course, is yes. And one way of constructing non-invertible symmetry is a condensation introduced in this paper. And I guess that Davide Gaiotto will talk about it in detail later. However, let me introduce it briefly here. Suppose that you have an finite invertible p-form symmetry in your theory, then pick some submanifold of your spacetime, take its tubular neighborhood, and gauge this invertible symmetry on this neighborhood by imposing the Dirichlet boundary condition on the boundary, and that effectively defines our topological operator, which is called the condensation. And in particular, when this sigma is codimension 1, then the boundary of this neighborhood, it becomes a topological interface between your theory and its gauged version, assuming that the symmetry is non-anomalous. And this condensation is the fusion of this topological interface and its dual. In most cases, this defines a non-invertible and indecomposable non-invertible operators. And while this should be interesting, this does not essentially carry any information beyond the original invertible symmetry. Therefore, we also would like to ask, is there a non-condensation, non-invertible symmetry? And one example can be found in the statistical model, which is similar to the 2D Ising model. So here we put the spin on each edge and assign the boson weight to each bucket like this. And this is static model. And this model have Kramers linear-like duality, exchanging high temperature and low temperature. And the dual theory is actually the Z2 form gauging of the original theory. Therefore, we have an interface connecting the two theories, topological interface. And at the self-dual point, this interface becomes a self-interface, or in other words, becomes a non-invertible symmetry with fusion law and squared equals to the condensation of this one-form Z2 symmetry. Okay, and this is non-invertible. So on lattice, this paper explicitly studied this non-invertible symmetry, and also there's a beautiful bulk boundary perspective in terms of the 4 plus 1 dimensional Z2 gauge theory explained in this nice paper. And this perspective is also related to Shao-Wen's and Ryan Thorngren stocks. And this model has first order phase transition at the self-dual point. However, with the ZN version with higher n, these old papers suggest there a gapless regime in the parameter space. Therefore, it would be interesting to investigate further using the current techniques. Finally, let me comment about the Continuum Kft. So even for the Continuum Kft, we can find some self-duality upon some gauging. And for example, the pure SO3 Young-Mizar theory equals to pi. If you gauge the Z2 one-form symmetry with particular digraph twist and do the time orientation reversal, then this operation brings this theory back to itself. Therefore, there should be a corresponding non-invertible anti-linear symmetry in this case. And this should be the UV version of what this paper considered. You also get the non-invertible symmetry by gauging non-abelian finite group, even in higher dimensions, and one of the examples is proposed in this paper. But these examples are related to gauging of invertible ones. So one might ask that is there any more exotic one, or even is there a continuous one? And these are interesting open questions, and you should refer also to these interesting talks. And please notice that I haven't answered my first question of are they good for anything, and I cannot answer, but I hope that this turns out to be positive in the near future. So far, I've been talking about bottom-up approach, finding some model with some non-invertible symmetry, but we can also start from problems. That is that there are known unnatural phenomena in QFT from Wilsonian viewpoint. And in 1+1D, there's one such example in adjoint QCD, and as Zohar talks, it can be explained by non-invertible symmetries. But in higher dimensions, there are also some phenomena that looks unnatural, and non-invertible symmetry might be a reason. Okay, so thinking about it might be fruitful. I've said what I wanted to say. Thank you for your attention.
Look you in the eye and then grill you. Yeah.
I'm interested about this question of whether there are, in 4 dimensions, non-invertible symmetries that do not come via gauging, because the one we studied is also like via gauging, and I don't know if you have thoughts about it.
Well,
someone.
Well, but maybe use the microphone. Yeah.
Could someone repeat the question? It wasn't very understandable.
The question is, in 4D, can you have a non-invertible symmetry not from gauging, but from some other constructions? I think that depends on what we mean by from gauging, right? So in 2D, a general statement is that if you have a CFT that has a Z2 zero form symmetry, and if you gauge that Z2, the CFT goes back to itself, then there is a non-invertible defect. You can say that comes from gauging because you can go away from the fixed point and build a gauging interface. In 4D, I think there's something similar, and that's what Kantaro was saying. You can take any 4-dimensional theory with a Z2 one-form symmetry, and suppose if you gauge the Z2 one-form symmetry, it goes back to itself, then there should be this Kramers-Wenier defect. I don't know other constructions.
Yeah, so there's the result about the 4D TQFTs that I mentioned. There's like similar results in 5D. It's not. I don't think it's as trivial, perhaps, but I think these theories, like if you say something like the bulk TQFT is always a gauge theory, then I think you learn something that, like, in some sense they always come from gauging. Like the Mourinho Equivalence classes can look like things like Shu-Heng mentioned, where you have some kind of duality under gauging. It's not literally a group like Symmetry, but still comes from a group. It's like weakly group theoretical. In 2D, in fact, there's a conjecture that if all of the quantum dimensions are integers, that the fusion category comes from some kind of like iteration of this procedure of studying self-dualities under gauging. Like it's an iterated group extension. So yeah, I don't know. I don't feel qualified to give an answer, but I hope that we find an example.
I have a question from Edinburgh. It's about the statement on Mourinho equivalence, right? Mourinho equivalence typically is a derived equivalence between representation categories. And is there an interpretation of this? I mean, can you clarify a little bit how that it is derived is with the structure of the classification of the symmetry?
Yes, well, it's very easy to derive from the definition I gave you of AM, because M itself forms a bimodule. So AM is the commutant of A acting on M. And then once we have a bimodule between, say, two rings, the most familiar case, then we get a map between their module categories by tensoring with the bimodule over the ring. Sorry, but that's the math answer. The physics answer is that when the module categories, like the category of module categories, is the category of boundary conditions of this theory, and we have this perhaps stronger statement that well, I don't know if stronger, but we have the statement that the bulk TQFTs only depend on the Mourinho equivalence class. So of course they have the same boundary conditions, and the module from the module M itself, you can construct a defect that realizes this, and that gives you this duality that I said.
I have a naive question for Ryan. So the question is about what does bulk boundary correspondence mean in higher D? And let me elaborate on my question. So let's say we start with 2 plus 1D TQFT. The 2 plus 1D TQFT admits many different boundary conditions, infinitely many. We can always put a 2D QFT on the boundary and get a new boundary. But of course, we can limit ourselves to topological boundary. And we can further restrict ourselves to a simple topological boundary condition that doesn't have degenerate ground state. And then there's classification for what kind of simple topological boundary conditions you can have for 2 plus 1D TQFT. But now let's say I go to one dimension higher, I mean 3 plus 1D. But for any topological boundary condition of a 3 plus 1D TQFT, I can always stack another 2 plus 1D TQFT on it. And that will give me a new boundary. So I'm just curious, like, given a 3 plus 1D TQFT, there seems to be infinitely many topological boundary. So with that caveat, how does the bulk boundary correspondence work?
It's a good question, I think. So in 2D, there aren't many interesting 2D TQFTs. Of course, you could try to do the same thing, but they're all sort of like, they mean your theory is reducible, right? They're all given. There's only local operators that you can just diagonalize. Maybe you want to say something like that in 3D. I mean, I really don't know. I'm trying to be like, I don't have the answers here. I'm putting the questions out. So maybe you want to factor off these TQFTs that you can just stack. Like maybe they're not interesting, or maybe it's related to this idea that perhaps all of them are Mourinho equivalent. Like maybe it just doesn't mean anything to think in terms of this. I'm trying to convey that you should not be dissuaded by the lack of interesting 4D TQFTs in the search for categorical symmetries. Theo?
So sort of half for Shu-Heng and just sort of for all of you. So there's something I realize I'm just confused about, which is we've all been talking about how like having symmetry means I live on the boundary of a topological field theory. But if I have a continuous symmetry, there's things that there's no debate that things can have continuous symmetries. If I were to try to build a TFT one dimension higher from that continuous symmetry, it very well might not be a kind of full TFT. It might the path integral I try to write down might just be a terribly infinite thing. So how do I kind of compare the sort of picture about continuous symmetries, about Lie symmetries on a quantum field theory with something like how Ryan was talking about living at the boundary or something? I didn't understand the question.
Maybe repeat the question.
So the question is about how to do something like bulk boundary correspondence for continuous symmetries, right? I think it's even a question for ordinary group-like symmetries. There's of course, we have some notion of SPT phase for continuous symmetries, but once you gauge that symmetry, which is like what we were doing in this bulk boundary correspondence, then yeah, it's not really topological theory, unless you're lucky. Some Chern-Simons theory happens to be topological. Yeah, I think it's a great question. I think it shows that maybe this bulk boundary correspondence is not the complete perspective, just one perspective.
Just a trivial comment that I don't think we necessarily need to couple to a bulk, right? If someone hand me a quantum system in its own space-time dimension, I can just study its global symmetry, its categorical symmetry, and all of their anomalies on their own, right? Sometimes it's convenient to couple it to a bulk, and that makes some aspects manifest, but it's not necessary.
Let's take some of the questions from Zoom. Davide, you have a question?
I think Nadia is the sense first.
Okay, Nadia.
Oh, thank you. There is an advantage of being older. So I've been outside this thing for more than 30 years, so I'm totally out of date, and I would like some refreshment. So there was a statement here that all topological field theories with some supplementary conditions about what you really mean by topological field theory in 4 dimensions is essentially a gauge theory. So I understand this was proven. What is the status of the corresponding statement in 3 dimensions? The reason well, maybe I shouldn't even say why I asked that. What's the statement of the corresponding statement in 3 dimensions?
Well, first, they are not all gauge theories.
Well, it means, no, if we include Chern-Simons.
How do you know?
Oh, you move Chern-Simon. They are not all finite group gauge.
Yeah. When they said gauge theories, they meant finite group gauge theories in 4 dimensions. Finite group.
But what is to put things in perspective, more than 30 years ago, Greg and I conjectured that all of them are Chern-Simons theories for some group, perhaps modding out by one-form symmetries, etc. And we looked very hard for counterexamples of that, but I think we stopped looking more than 30 years ago, and I'm sure there's been a lot of progress since then. So is there any counterexample to that?
Maybe someone's been following this like Hagerup story.
No, Hagerup doesn't admit braiding. It's he's talking about 2 plus 1. Oh, you take them. It's not known, yeah. Yeah, it's an open question. It can be a product of many gauge groups, and then you quotient by something, and
Yeah, it could be very complicated.
yeah.
I can give a quick comment on that. If there's none of the authors are here, there are recent papers that saw criticality in a spin in an Enneon chain, if you wish, that was built on Hagerup. They saw C equals 2.
That's in 1 plus 1.
But
yeah.
there's no as of that seems to conflict with the predictions. There's been guesses of what the Hagerup CFT would be, and that's C equals 0 mod 8. And so obviously 2 is not 0 mod 8, and it's not clear that this is even an exotic CFT. Maybe it's a normal one. But anyway, I think that's what someone meant. That this is just as within the last few weeks on Hagerup. So I think to answer Nadi's question, I think the conjecture you and Greg made still stands. I don't think anyone has any counterexamples to it. And
I can add to the extent that I couldn't attend all the talks here, but to the extent that over the last few weeks I read a little bit, all these fancier procedures of gauging, condensation, zesting, and all that, all this is just changing the gauge group along the lines that Greg and I studied. And I just confirmed some of these things with Greg to make sure that I'm not completely off base. So I'm surprised that over more than 30 years, there are no counterexamples. Maybe Greg can shed some light on it.
No. I asked the same question, Nadi, within the meetings of the collaboration earlier. And no,
Yeah, the category people, for example, like Zhenghan Long and crowd, some of whom were here, you know, started out classifying all the categories all the modular tensor categories they could find with certain number. I forget, are they up to 6? Someone here will know. 6, I think, at least, maybe 7 now. And in the hope that, again, something would pop up that you and Greg didn't know about, or at least implicitly, and nothing yet has come up.
Okay, let's
I can say that over the years, people from Station Q have come to me and saying, ho, 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 I have this modular tensor category, which doesn't fit your picture. But I've never been convinced.
No, and that oscillates in time too. They shoot them down and then they come up with another one. Which is great, but nothing has stuck.
Okay, let's take Davide's question.
Okay. Right. I'm not sure it's a question or a comment. So just say that you don't even need to go to continuous symmetries in order to get in trouble with the gauging in the bulk idea. I think if you look at E8 at level 1 and look for topological lines in E8 at level 1, you can find huge amounts of them, way too many to fit inside a fusion category. And so you cannot really couple it to a gauge theory, to a topological field theory in one dimension higher. So, I mean, these are probably somewhat peculiar examples, but they are there.
Add a comment because some confusion in the previous discussion between what's called in math the width group of modular tensor categories versus three-dimensional DQFTs. Most Turaya-Biro theories are not gauge theory, don't come from a... Most Turaya-Biro theories are not gauge theory, don't come from a group. They might come from a finite semi-simple Hopf algebra, so if you can think of that as a generalized quantum group, that's fine, then yes, the gauge theory. But aside from that, there are lots of three-dimensional theories that are not gauge theories. The question that had to do with what Nathi and Moore did was whether up to those that we know, there are any others beyond the Chern-Simons theory. So that's a different question. It's a question about equivalence classes of modular tensor categories, not about three-dimensional TQFTs. I just wanted to clarify that point. And the other point I want to return to even more was Theo's question.
Can you clarify again what you just clarified?
There are, one sentence. There are many three-dimensional TQFTs that are not gauge theories and have nothing to do with the group.
But in the language we've been used,
they're not continuous either.
Has been discussed of higher symmetry. They are gauge theories if they are Turaya-Biro.
Yeah.
Because as soon as you have a fusion category, the quantum double is the gauge theory for the fusion for the higher symmetry. Non-invertible symmetry.
But if you talk about non-invertible symmetries,
it's so easy to prove that something is not associated with the group.
Maybe Zohar,
because in many cases, if you look at the TQFT, it's not easy to identify which gauge group of Chern-Simons theory this thing can come from. And in fact, the answer is often not even unique. In cases we know many different Chern-Simons theories that lead to the same TQFT.
Nari is talking about continuous symmetries with Chern-Simons terms, not finite gauge, not finite gauge theories. Turaya-Biro theories are not always finite gauge theories. That is correct. But every known three-dimensional TQFT has so far been possible to represent as a continuous gauge theory with a Chern-Simons term. Including non-abelian, including Turaya-Biro theories that are not finite gauge theories.
Let me just clarify what Zohar clarified. When you say he said continuous, what he really meant continuous or discontinuous. So the continuous or finite, for example, the gauge group would be O2, which has a continuous component, but also some discrete part. But there's a group, and the group might be continuous or not. And there are some levels, all the possible levels that you can write, including the Dickerf-Whitten twist and other things. And the question is, does this cover all cases?
I believe Konstantin answered and said that does not cover all cases. An example is the derived VRO theory associated to some very exotic fusion category, such as, for example, the extended Hagerup fusion category. So the corresponding modular tensor category is the double of this very complicated fusion category. That fusion category is not related to a group in any sense. I mean, you could call it a categorical analog of a group, but it is not a group.
How do you prove that?
I hope I said something that corresponds to what you said, Konstantin.
Yes.
No, but you have to prove that. You have to show that no matter which group you will take, it cannot be obtained from that group with some Chern-Simons terms. It's not been shown.
Maybe we can. I have a question for Zohar. You said you had, in your example, many hidden lines. How do you go about finding lines that are hidden?
Well, so the reason that we started working on that two-dimensional model was because of this unnatural phenomenon that Kantaro briefly mentioned. So in that theory, there is a quartic fermion interaction, like psi plus, psi minus, and people computed its beta function and found that it's 0 at one loop for no good reason. And then there was a follow-up paper that found that it's 0 also at higher order, and it looked mysterious. Like usually in quantum field theory, you generate every operator that's not protected by the symmetries. And that operator was not protected. Okay? So the only way, so the idea was to try to explain that with non-invertible symmetries. Now, the way you find these non-invertible symmetries is related to what Nari said about G mod G. So you can think about these models as not G mod G, but something a little bit more exotic with some kinetic term for the gauge field. So if you find topological line defects which commute with some currents, you can argue that they would survive gauging if there are no anomalies. So you find some topological lines in some quotient theories, in coset theories, and then you have to look at a subset of those that commute with the kinetic term. And then you know that there are symmetries of the full theory at any energy scale. So it's not enough to look at G mod G, you have to do something more.
We were saying lines that survive gauging SUN.
Yeah, for instance, you can consider the quotient SO8 mod SU3. It's a gap theory, but now you add the kinetic term for SU3. So you have to understand how many topological lines would survive adding a kinetic term. Most of the lines of SO8 mod SU3 will not survive. You have to find those that do. And that's what you gotta do to find the non-invertible symmetries at all scales.
You know how to answer Shu-Heng's question about the current on the line?
Oh, you are asking if to prove that it's exactly marginal? Yes. Well, that's just a question of computing the three-point function. It should be trivial.
No. If you look at any points on the moduli space, it's that. If you look at every point on the conformal manifold, that's it.
But having exactly marginal doesn't mean it will preserve the topological nature. You can have exactly marginal deformation taking you to a conformal line.
Yeah. So
preserve the topological nature of the line.
Right, you have to prove that there is no displacement operator. So what I said is that to prove that it's exactly marginal, it's just one computation. It's a three-point function. It's probably trivial. To prove that the line, proving that the line remains topological amounts to proving that there is no displacement operator. And that's also a computation in conformal perturbation theory. So it's another three-point function. So I think it should be easy.
Actually, can I make a comment about that? So actually, in this case, it's kind of trivial because the spin is fixed, and the spin will not get normalized. Yeah. So once you show that the operator retains its dimension of the deformation, so exact marginal will be
so it should be one computation, should be very easy.
I'm surprised that there needs to be a computation to check the topological nature. Right?
Yeah,
in ordinary symmetry, you don't have to check anything.
Yes.
You have a conservation equation, you're good to go.
Yeah, it will probably be also a one-liner.
No, here we have to see the three-point function.
We have examples where, in some cases, this marginal spin one operators on the line will be lifted. Some examples they won't.
But it boils down to one three-point function.
Right? Yeah, it's always some computing three-point function.
Okay.
Okay, so maybe let's wrap up here and thank everybody for the discussion.